What's up, everybody? I've got a motherboard on the bench today. This is a FIC or FIC, First International Computers, 486-GIO-VT. It uses the VIA 486A chipset paired with the VIA 82C 482 VLB to ISA bridge. It's got onboard IDE courtesy of this Promise VLB IDE controller chip, and it's got some Super I/O functionality with these Winbund thingies here. And this board had a fault of no post, but it turns out that was actually just missing jumpers. I got this board without any jumpers and without a BIOS chip, and without cache for that matter. It's got a pretty peculiar problem. Let's turn it on and see what it does. So at first everything seems normal. RAM counts up, you enter the BIOS, you do some stuff. And no problem. Set some values in the BIOS. You actually save it. Everything appears to be fine. You end up here, do some stuff, blah blah blah. Then you turn the machine off. Turn it back on. Everything seems to be normal, but you go into the BIOS and it freezes. Either it freezes or it forgets everything. Yeah, sometimes it freezes when you select the option in the BIOS, or it forgets everything. And you see it just froze, and suddenly 24 minutes, 1 second. Something's really not going right with this RTC chip. But this is a known good chip, right? This is an NWX287 that is known to work in other boards, right? So that is not the problem here. Right, okay. Here is the datasheet for the 12887 real-time clock, which this chip replaces, I guess. We can have a look with the scope on all of these signals, right? We need the multiplexed address data bus to be intact. We need chip select to be intact, address strobe I suppose, data strobe I suppose, and this one's especially important, read write, because if you have the writes toggling instead of reads or something, that would obviously be bad. If you've got a problem distinguishing between address and data, that would obviously be bad. If the chip is stuck in reset, that would obviously be bad. But I don't think that's happening here, because else I suppose it wouldn't even pass the RTC check in the post. But yeah, let's just quickly probe these signals. Right, so I got the oscilloscope here, and I'm gonna probe some pins here on this RTC. On the other camera, I'm just gonna zoom in here on the pins that I'm gonna probe. The address lines. Yeah, that one's good. That's 81. 82, 83, 84, 85, 86, 87. Yeah, those are all good. Got the chip select here. It's permanently selected, I suppose. We've got the address strobe here. Yeah, it's toggling a few things. What about read write? Oh, that's looking a bit weird. That's strange. That doesn't look good at all. Look, it starts at like 1.5 volts, and it's fluctuating very weirdly. Look at that. It could be it could be that the pin is floating. This is weird. I need to trace where those signals go. Yeah, the socket is a bit iffy because I didn't have the right size, so I just cut it. Don't really care, as long as it works. But I'm worried about this corrosion underneath. That must have gotten worse after I socketed this. Let's first of all check the resistance between these strobes and VCC to see if they're pulled up. Here, the read-write one. That's mega ohms. That might have to be pulled up. Actually, we can check this. I have here a motherboard, also made by FIC, and has the same chipset. So we can just probe the pins here. Read write signal. It's 10 kilo ohms to VCC. Yeah, DS data strobe. That also has a pull up. The read write strobe is connected to a resistor pack right there, which is a resistor pack probably to 5 volts. We find continuity on the common pin of this resistor pack. So yeah, there's a 10 kilo ohm pull up on the right strobe, and we're not seeing that on this motherboard. Yeah, there's probably a resistor pack much like that one somewhere close by. I'm guessing probably that one, because it's the closest and it also has the same amount of pins. Actually, we should probably just check if there are any strobes that are pulled. Yeah, the data strobe has a pull up of some sort. Let's see if it goes to this resistor pack. Yeah, it does. So that's exactly the arrangement we would expect after looking at the other board. What about the read-write strobe? It actually does go to this resistor pack. Is the resistor pack bad? Because there's no pull towards 5 volts here. 10k, 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 22k. I think this resistor pack is bad. Like, it's normal that you can see a lower resistance to the common pin. Yeah, that's not surprising. That can happen if there's other things in the circuit that pull it closer to the voltage. But a higher resistance definitely shouldn't happen. Here's the dodgy resistor pack. Let's check out the markings first of all. 103. So that's a 10k resistor pack, as with the other board. That's interesting. The resistor pack is actually fine. Either that or heating it made it go better. Do you think heating it actually improved it? Or was there maybe a cold solder joint? I'm utterly perplexed. Solder those 2 pins back. See if we still get that weird reading. That would be very strange. Now I'm still getting 10k. I don't know, I'm not trusting it. Okay, since it's too big, here's the hack that I actually came up with. I soldered it to the back of the board. Doesn't really matter. Changes anything, I will replace it with a proper one. So let's just briefly put it back together. Actually, let's first check the resistances towards 5 volts. Yeah, that looks okay now. All the strobes now have regular kilo ohms towards 5 volts, so that's okay. So these look much better now on the meter. The question is, did it change anything? Okay, so we're back in the BIOS. This is the read/write strobe. It still looks like crap. So the resistor pack wasn't bad. I think we need to follow where that signal goes. Just for reference, I'm gonna connect up the other board and see what the signal looks like on that pin. And yeah, I don't really have a proper ground for this, but doesn't really matter for this test. And if I go to normal mode on the scope, we should be able to see an activity when we save something to CMOS. Yeah, there we go. That's what it should look like. And that's much cleaner than it is on the other board. Yeah, this is a lot cleaner. There's something wrong with the other board. Okay, now we've established that much. So now we need to trace where those signals go. Okay, so on the other board, that signal goes to a data buffer right over here. Yeah, all go to the same buffer. So let's find a buffer where those signals may be connected to over here and see if there's perhaps something wrong with it. I would wager that it's probably going to be one of these here, since they're in a very similar location. I can't be sure that there isn't a break in the tray somewhere that's causing the problem. So I'll take a signal that I know is probably okay. Ah, there. So that signal does actually make it to a buffer. Alright. This is pin 3, the signal we know is bad. It makes it to a buffer right over there. So we need to check what it is. It's probably 244 or 245. It's a 244. So, what pin is it actually connected to? It's connected to pin 3, which is the output 4. So we need to check output enable 2 and input 4. That, yeah, it's acting weird. Now, here comes the interesting bit. What's happening to input number 4? Aha! Things are actually happening there properly. What about the output enable 2? Things are happening there too. So the input signal is reaching it and it looks beautiful, and the output signal looks like this. That is not normal. This chip is bad. I think we need to replace it. Clean extraction right there. No problem at all. Would you look at that? I have a scrap donor board here that has an F244 here. Yeah, that looks okay to me. Let's take a look again on pin 3 of this IC. What the fuck? I am completely perplexed. What is this? Well, I'm gonna continue tomorrow and see what the fuck is going on. Okay, so I've desoldered the socket. It's kind of disintegrated, but whatever. Cleaned up all the corrosions, resoldered all the pads, everything. And let's see what this thing does now. Put our scope probe on. It's nice and clean. Now let's switch our oscilloscope to normal mode. Save and exit and see if we get a right pulse. And we do. Now let's switch the machine off. And switch it back on. And see if we retain CMOS. And we do. Would you look at that? Perfect. Well, I'm not really sure if I would call it perfect, because I essentially spent 2 hours the day before chasing 2 red herrings. Yeah, because it exhibited symptoms that led me to a resistor pack that looked faulty but wasn't. It led me to a buffer chip that looked faulty but wasn't. And that's really a cool thing, because I actually learned something here to not second guess myself and actually take a look at obvious problems first, such as the corrosion on the board, which was the culprit here. There may have been a fault with the socket or with the soldering, because even with the corrosion in place, I don't see why the resistance would suddenly go up to 22K on that resistor pack, or why the pull-up that was obviously present physically was not readable on the chip or the socket itself. There could have been one problem that was actually present here, but was masked by other things. But the main problem here that was causing the faulty signal on the right strobe was definitely the corrosion that was on the board. So, what else can we do with this board? Well, I can replace this broken VLB socket. In fact, the scrap donor board that I already used for parts has a few sockets for me to take off. The other thing I need to do is flash a new BIOS chip, because the BIOS chip I've been using for this one is my troubleshooting chip, which has these pin headers soldered to it so I can connect a logic analyzer. Let's see if we can detect a hard disk and run some tests. IDE HDD auto detection, yeah, that works flawlessly. Yeah, it's running at 25 megahertz because I didn't jumper it correctly. Yeah, let's see, we can do cache check. Cache doesn't work. Did I jumper it incorrectly? Okay, I put some cache chips in that I got from another scrap board. These are 8 256 kilobit chips, so 256 kilobyte cache. To jumper the cache for that, you need to set JS1 to 2.3, JS2 to 2.3, and JS3 to 1.2, which, as you can see, I have done 2.3 to 3, 1.2. Now we should have 256 kilobytes of cache. Yep, there we go, 256K. Cache is 256 kilobytes. There we go. Perfect. So, last order of business, let's replace that broken VLB slot. Oh, it's already coming out. Oh, that's good. No residue. No broken wires. No broken pads. There you go. I mean, probably this still would have worked, yeah, but it's just really ugly. And potentially it might break. There we go. That's what I'm talking about. Color-wise, it's a pretty decent match, even if not a perfect one. So should I leave that bodge in place? Probably not. There we go. Right, before we call it quits, let's briefly put a new flash chip in there. Winbond W29EE011, 1 megabit. Flash, Winbond 29E01, DIL, erase. Data buffer, load. Alright, program. Done. Nice. Okay, quick check if it still pulls before doing the VLB test. And it does. Good. Here's a Cirrus Logic VLB graphics card. Looks good to me. I don't know about you. But that is definitely a picture coming from a VLB card in the slot that we replaced. Good stuff. Let's put the thing in the database. We've got a FIC 486 GIO VT with a via a VT82C 486 GMC socket 3. Oops, AT with VLB and ISA working. Placed VLB slot. There we go. So, to summarize this repair, what could I have done better? I could have maybe not second guessed myself by actually checking the corrosion under the socket first. I don't remember if that corrosion was already there when I placed the socket. Maybe it looked okay, so I placed the socket. I could have saved myself all the troubleshooting on the buffer. Other than that, that was just a little video to walk you from start to finish through a troubleshooting process on my end, without much editing or additional commentary, just to give you an idea on how I actually approach these things. So I hope I see you next time when I take a look at another old piece of hardware, maybe a motherboard, maybe something else. We'll see about that. Catch you later. Bye bye.